So I'm charged with the task of telling you what quantum technologies can do for machine learning and AI in the very near future. And I have some good news and I have some bad news for you. I'll start with the bad news. The bad news is that we are exactly as far from building a quantum computer as we were 5 years ago. And when I say that, I mean an idealized version of quantum computing, which is fault-tolerant, scalable, and universal in a very well-defined sense of the word. And the good news is that we made rapid advances in something less. Something that is imperfect, it's not quite fault-tolerant, and it's not quite as universal as we want it to be. But now there are a whole lot of companies building such imperfect quantum computers. The oldest player in the field is D-Wave. Then we have some big players like IBM and Google getting into this game. And we have a range of startups like IonQ, Rigetti, or Xanadu who are building quantum computers using various competing technologies. And the second good news is that these early imperfect quantum computers are useful for certain kind of machine learning applications. So we expect that within 4 to 5 years, we will see some quantum lift from using these technologies in particular machine learning applications. So what can you expect and what you cannot expect? So if you have an existing machine learning pipeline and you have a GPU cluster running some big deep learning architecture, you can keep it. Like you can't just replace your GPU cluster with a quantum computer and make it run exponentially faster. That's not how it works. You have to select a particular set of machine learning algorithms that can get any kind of advantage from using quantum computers. So in this sense, these machine learning techniques and quantum machine learning do not compete with your existing machine learning framework. It's more like it enables certain technologies that you were not able to use until now. So it's more like a complementary technology rather than a replacement. And what we are aiming at is a constant time speedup. So you probably heard about claims about exponential and quadratic speedup. What's realistic in the near term, and I talk about 5 years, is a constant time speedup. So that doesn't sound like much, but think about what enables deep learning. GPUs run these deep learning networks about 20, 50 times faster than a regular processor. And without that, you would not have deep learning architectures. And we look at the same kind of speed up in these particular applications that we're targeting with quantum technologies. So what are these applications? Well, the most natural thing to do on any kind of quantum system is sampling. So when you, as a classical observer, interact with a quantum system, what you do is you sample. And sampling is extremely useful in probabilistic machine learning models, probabilistic graphical models. These are quintessentially generative. Think about macro-random fields, think about Bayesian networks, think about Boltzmann machines. But if it's too abstract, I put it into context. So right here in the Creative Destruction Lab, we are incubating more than 20 quantum machine learning startups. And I'll give you an example of one of them. It's called Netromark. They have an intricate machine learning pipeline, which includes deep learning. It includes various manifold learning methods. And the small component is sampling. It's a probabilistic model to model patient data. And they are doing drug resurrection and drug development in phase 3 trials. And they expect that just by having this small component, a small quantum machine learning component in the entire ensemble that they are building, they will get some 10% increase in their prediction accuracy. The second example is optimization. And you might say that your backpropagation is eventually just stochastic gradient descent, so it's a kind of optimization. And I told you that you can keep your GPU cluster. And there's no contradiction. So the kind of optimization that you can do on a quantum computer is very different than what you can do on a GPU cluster. The data has to be sparse in a reasonably well-defined sense. And it also has to be a hard optimization problem, also in a reasonably well-defined sense of the word. But to put this into context, I give you an example of a second company that we're incubating here, which is Quantum Meta AI. So this company takes fundamentally different learning modules together. So you can have a feed-forward neural network, you can have a recurrent neural network, you can have some quantum-enhanced Boltzmann machine. And orchestrating these different learning modules to achieve a task is exactly the kind of optimization that will work well on a quantum computer. And that's exactly what they are doing. So these two examples, sampling and optimization, are similar in the sense that you start with classical digital data, you end with classical digital data, and there is something quantum in between. My last example is different. So in the last example, you really have to work on quantum data. And where do you get quantum data from? From quantum simulations. So in this case, you are looking at some quantum systems, say a set of particles, and quantum systems explode in complexity very fast. So what we can simulate classically is extremely limited. It's just a few particles. So what we do is we build a quantum system that we can control to simulate one that we are interested in. So here the data is quintessentially quantum. And now you can ask yourself that, hey, can I use machine learning here to, for instance, to drive the discovery of new materials? And the answer is yes. And this is one very important application area of quantum machine learning. And again, to put this into context, we have a company being incubated here called Protein Cure. They studied the protein folding problem, and they do various simulations on different quantum computers to understand protein folding better and develop protein-based drugs. So with that, I conclude. My take-home message is that within about 5 years, you can expect some kind of a lift from quantum technologies in search and machine learning applications. And we are betting on this by incubating quantum machine learning startups right here in Toronto. Thank you very much.